Of all the great hunters, of all the predators that stalk the planet, one has taken more human lives than any other: the mosquito. They annoy us, they attack us, and they make us itch. But more than that, they are unwitting killers. Each year, all around the world, 700 million people are infected with a mosquito-borne illness. 3 million of them die. The numbers are rising, and the diseases are spreading. We are caught in a battle against the mosquito. A race against time to learn more about this formidable foe, an enemy with a thirst for blood. As long as people have walked the earth, there have been mosquitoes here to plague us. In fact, they've been around and biting for more than 50 million years. Today, they bear more than 100 diseases, many fatal, all transmitted through their simple bite. Over the course of history, mosquitoes have wreaked havoc on human civilization, and we've helped them along the way. In the 17th century, the shores of the Americas were invaded by mosquitoes carrying yellow fever. Crossing the Atlantic on slave ships from Africa, the mosquitoes thrived, spreading yellow fever across the land, filling cemeteries with their victims. Another international killer, malaria, has long been one of the hardest diseases to combat, let alone defeat. A burning fever that often leads to death, it still claims lives around the world. Dengue, or breakbone fever, is making an alarming comeback in a version that can kill in hours. In the past year alone, tens of millions of cases were reported. Researchers are worried because mosquito-borne diseases like these aren't going away, and the poorest countries in tropical regions are suffering the most.
Okay, look at what? Look at this. I catch 2 mosquitoes here.
Out on the front lines, putting themselves in harm's way, are the entomologists and molecular biologists dedicated to defeating this tiny foe. Whether in the lab or out in the field, they're pursuing the mosquito. Battle-experienced soldiers ready for war, tracking, testing, attacking.
We have to know our enemy. We have to know how to exploit what we know about its life cycle, what we know about its behavior, what we know about its daily life, which will help us to really devise better strategies.
Perhaps the best place in the world to learn about this insect is a site with more mosquitoes per square foot than anywhere else on the planet. The perfect breeding spot. Mosquito heaven, the Florida Everglades. It's summertime. Hot and humid, the height of insect season. The mosquitoes are out in force. Most people would be running away, but not these two. Mosquito ecologist Phil Lunabus and control expert Alan Curtis.
We're on the coastal prairie trail in Flamingo, probably the highest populations of mosquitoes anywhere in the world. We're experiencing something about a 500 a minute landing rate. And being here for several minutes, we're probably going to blood feed 5,000 or 6,000 mosquitoes in a very short period of time.
I'd say, judging from the competition, that I'm winning right now.
Yeah.
Probably I have about 200 mosquitoes here, and we've only been here 30 seconds. This is what Florida will be like without mosquito control.
They're bearing their legs to the salt marsh mosquito, an insect that doesn't carry human disease, but is known for its fierce bite and for being a major pest. For 20 years, Curtis has been coming to the Everglades to collect mosquitoes for his research. Lunabus is here to study the habitat where they thrive.
This is the easiest way to collect adult salt marsh mosquitoes is they're coming to one of their preferred hosts. And it's pretty simple to collect them off of an individual standing here because the mosquitoes are drawn to Phil and to the black fabric on his shoulders. And it's real easy to collect 10 or 20,000 of these mosquitoes in just a matter of minutes.
The Everglades aren't the only place Curtis and Lunabus search for mosquitoes. These highly adaptable insects have proven they can take advantage of almost any environment, particularly those made by humans. On nearly 1 million acres in Florida alone, people aren't just raising grapefruits and oranges.
If you were trying to design a habitat for a mosquito, you couldn't do any better than designing a citrus grove. The problem here is the water table is so high that they had to protect the trees, and that's why we put trees up on beds. And the furrow in the middle is where the rainwater collects, and this was a perfect man-made habitat.
These furrows are full of larvae, mosquitoes in an early stage of their life cycle. Curtis doesn't have to pan deep to collect them.
We found that from a single flooding of a citrus grove, it'll produce 47 pounds of mosquitoes per acre. And that equates to something like 1 billion mosquitoes per acre.
Whether in natural ecosystems or human-made, mosquitoes thrive in every corner of the earth. From the jungles of the Amazon to the Louisiana bayous. Across the plains and mountains of every continent except Antarctica. The mosquito's ultimate survival depends on heat, food, and above all, standing water. Find water and you'll likely find the mosquito. Reproducing, adapting, evolving. In fact, the mosquito is not one animal at all, but 3,500 different species. About 20 more are being discovered every year. Some are black and white striped, others golden brown. They can range in length from less than 1/10 of an inch to 3/4 of an inch. Not all carry disease. In fact, only 10% do. But all mosquitoes are members of the fly family and share key characteristics. A single pair of wings and 6 spindly legs make this stealthy stalker highly mobile in the air and on the arm. The mosquito lands gently, often imperceptibly, and makes its escape, lifting upwards in almost any direction. Covered in iridescent scales, its wings beat up to 600 times a second. That's 10 times as fast as a hummingbird, giving the mosquito its distinctive buzz. On the hunt, flight is a zigzag pattern. Little bursts of acceleration over short distances. Top speed for a mosquito, just 1/2 mile an hour. While most stay close to home, some fly as far as 15 miles over the course of their lifetime. And that lifetime lasts, on average, only about a week. All mosquitoes feed on one thing for sustenance, the sugar-rich nectar of plants. Nectar feeding is the first act of every mosquito's adult life. As the mosquito crawls along a plant, receptors on the lower section of its legs act like taste buds, sensing carbohydrates, leading it to nectar. But the mosquito also seeks a more treacherous kind of meal, blood, ours. The bite is the sole domain of the female mosquito. Only the female of the species hungers for blood. She does it for one reason, to reproduce. Blood provides the critical source of protein she needs for her eggs to develop. So to help locate prey, the female mosquito has evolved a remarkable set of detection systems. Oversized eyes are made up of hundreds of tiny lenses, motion detectors that are most sensitive to the movement of prey. Palps are short-range sensors that act like a nose. They help the mosquito pick out the best spot to bite. But it's the mosquito's antennae that may be her most potent detector. These long-range sensors hone in on body heat and detect certain chemicals that all humans and other animals emit, like carbon dioxide and lactic acid. All of which combines to make the female mosquito a perfect airborne blood-seeking weapon. And she isn't afraid to take on monsters like us.
They are predators.
And if you see, the lion is considered a good predator, but it only goes after prey that is much smaller than they are. So I don't think they are very courageous. But a mosquito taking a blood meal is trying to take blood from animals that are millions of times larger than themselves. So I think they have much more courage than a lion.
It's not really a matter of courage. Her bite is purely natural instinct, one necessary step in a life of feeding and breeding. But before she takes her first blood meal, the female must do one thing: mate. Her distinctive wing beat attracts a male who latches on underneath her. For most female mosquitoes, mating happens only once. It may only take a few seconds, but she'll store enough sperm to fertilize anywhere from 1 to 10 batches of eggs that she'll lay in her short life, and add as many as 2,000 new mosquitoes to the planet. With her sex life over, the female begins the hunt. Predator and prey. In some species, the ever-prowling female can detect a meal as far as 100 feet away. Landing lightly, she starts quickly probing for a meal. A sophisticated set of surgical tools goes into action. They are housed in the proboscis, or snout, a full third of her body length. It's home to an entire arsenal of spears, saws, and blood-sucking devices. The proboscis is covered in a protective sheath, and with good reason. Inside are 4 tiny saws, 2 with serrated edges, each as sharp as a scalpel. The mosquito cuts just a fraction of an inch deep as she pierces the skin of her prey, searching for blood vessels. The lower part of the sheath bends backwards during probing. As she breaks through the blood vessel wall, saliva trickles down a narrow tube into the site. 2 pumps in the back of her head contract and expand, drawing blood up the proboscis and into her gut. This feat of evolutionary engineering pays off with a mere 1/10,000th of an ounce, but the female drinks as much as she can. She expels unneeded water even as she feeds, releasing tiny droplets and making room for more protein. It's all done so lightly, so quickly, and with a puncture so small, you don't even feel it at the time. But the mosquito is not just taking something out. She's also leaving something behind. Her saliva. The deposit of this complex mix of foreign molecules triggers an allergic reaction. But by then, the mosquito has already escaped. The result? Itching. Scratching. Sometimes the response comes only a few seconds later. Sometimes an hour. That tiny bump can torment you for days. But there's more to the saliva than just a bump and an itch. At the United States National Institutes of Health, José Ribeiro investigates the critical role saliva plays in the success of the mosquito's bite.
We ourselves are being injured, and we have mechanisms to prevent blood loss from injury. And the mosquitoes want to make us believe that there is no injury going at the place, and this is possible because of what they have in their saliva.
Mosquito saliva contains a storehouse of chemical weapons that block our body's natural defenses against intrusion. There are proteins that keep our blood vessels from closing as the mosquito feeds. Others prevent the blood itself from clotting so that it flows freely into the mosquito. Ribeiro has been studying saliva for 20 years, earning him the nickname Dr. Spit. But he's still trying to identify the exact chemical makeup of this key ingredient to the mosquito's bite. It's not easy to get saliva from a mosquito. In a half-inch insect, the glands are measured in microns, embedded deep inside the chest.
Hold the head and pull the head off.
When you remove the head, the glands pop out too.
Oh, this is beautiful. Just protruding from from the head. There are 2 pairs there. They both came out very nicely.
Ribeiro and his assistants will have to go through this process 1,000 times to harvest enough glands like these just to get 1 milligram of saliva, all for a single experiment. His team has isolated only 4 of the 20 or so key proteins in the saliva. But Ribeiro may be getting closer to the heart of a bigger mystery. While saliva is critical for feeding, it also is the conduit through which disease passes from one person to another. The mosquito is a vector, the scientific term for a carrier of disease. So when the mosquito bites, it may get more than just blood. If the person bitten has a transmittable illness, the mosquito may take in the disease-causing agent too.
When mosquitoes hatch, they don't have a little backpack of viruses that come with them hatching. They have to pick up that disease from either some animal or another human that has that disease or parasite to be able to transmit it.
These malaria parasites can be seen by first dissecting the stomach of an infected mosquito. Magnifying the stomach 1,000 times, the parasites appear as orange circles burrowed into the stomach wall. The black lines are air tubes, part of the mosquito's respiratory system. Malaria parasites remain in the stomach wall over a period of 10 days. On the 10th day, they migrate from the stomach to the salivary glands. Most mosquitoes are not affected by the parasite. It slips in unnoticed by the mosquito's own immune system and waits for an opportunity to invade another human.
So how can a virus get out of the mosquito and get into another person? They can go out by invading the gut of the mosquito and then invading the salivary glands. And when the mosquito start feeding on a person, not even start feeding, just lands and starts a bite, it's getting back into us.
Malaria, encephalitis, yellow fever, and dengue all use the mosquito as an intermediate host. Other transmittable diseases like AIDS have not evolved using the mosquito as a vector. The AIDS virus is passed directly between humans.
Probably the #1 killer of everyone in the world is malaria. It kills more than any other disease you can think of. It is transmitted by mosquitoes.
It's an old story. Back in the days of ancient Greece and Rome, many suffered from this illness they associated with the swamps. Over the centuries, malaria epidemics raged across the continent of Europe, reaching as far north as Sweden. Transmitted by the Anopheles mosquito, malaria is a serial killer, a tropical parasite for which no total immunity is possible. The human toll is enormous. Today, 90% of all malaria victims live in Africa, where 500 million acute cases are reported annually. Severe chills, recurring fever, these are the hallmarks of this disease. Kenyan molecular biologist Fred O'Doul knows all too well the ravages of the parasite he's fighting. O'Doul himself has been stricken by malaria 6 times.
You start off feeling feverish, where you have bouts of sweating, and then the temperature goes down again, and you get your joints very weak, and you have discomfort, like in your stomach, vomiting, headaches. The times when you even get hallucinations. And at that point is when you really feel like maybe you're going to die.
Every year, mainly in tropical regions of the world, malaria kills more than 2 million people. Most of the victims are children because their immune systems aren't strong enough to fight it off. And as healthcare professionals have feared, malaria transmission is only getting worse. Neither the disease nor the mosquito that carries it are going away. Every day, more and more mosquitoes are born, more deadly predators on the hunt for a blood meal.
Mosquitoes are probably one of the most explosive insects, maybe even animals, that you'll ever encounter. 6 or 7 days ago, you would not see a single mosquito, a single larvae. You get a rainfall, and all of a sudden, there are literally billions of mosquitoes here all at once.
For all of them, life begins the same way. After a blood meal, the female's eggs begin to develop. When her stomach turns white, it's time to lay her eggs. As she deposits them, each is fertilized by the sperm she's stored from her mating. She'll lay 30 to 500 eggs in a single batch, a floating raft of new mosquitoes. Different species have different strategies when it comes to egg laying, but all of them depend on, all of them need, water. Some lay their eggs one at a time in different sites just above the water's edge. Others, like the Mansonia mosquito, lay their eggs clumped together under the water. In tropical regions throughout the world, the Mansonia makes its home in the water lettuce plant. Putting her abdomen beneath the water's surface, she deposits a series of eggs on the underside of the leaf. Large tracts of water aren't the only place mosquitoes live and reproduce. In rainforests and woodlands around the world, many species take advantage of tree holes that collect rainwater.
We can have small tree holes that may hold only a few milliliters of water that only provide enough space for 5 or 10 mosquitoes, and then others that will have gallons and gallons of water and can produce thousands of mosquitoes at a time. So one of the things that's fascinating about tree holes is when you've seen one tree hole, you ain't seen them all.
What they all have in common is nutrient-rich water and a dark protective refuge to support generation after generation of tree hole mosquitoes. Mosquitoes even take advantage of water that collects high off the ground in hanging plants called bromeliads. Sometimes all it takes is a single ounce of standing water in a bromeliad to house the mosquito young. And many species of mosquito, some lethal vectors, have adapted to artificial tree holes, the kind you might find in a junkyard. One such invader was first discovered in North America in 1984 after hitching a ride in a shipment of rubber tires from Southeast Asia. It's known as the Asian tiger mosquito, a serious vector for dengue in that part of the world.
This is as close to nirvana as a container mosquito like the Asian tiger could find. These rubber tires, which fill up with water, are perhaps the best of all the containers in a junkyard like this, but use radiators, hubcaps, you name it, whatever will hold water here after rain, we'll find mosquitoes in it.
Here in North America, the Asian tiger does not yet carry disease, but at the rate it's breeding and coming in contact with humans, scientists believe one day it will.
Who knows how many eggs were in the initial shipment of tires? It could have been 20 or 30. But it rapidly expanded beyond the point that any mosquito eradication efforts were hopeless.
Wherever these eggs are laid, in tree holes, potholes, or rubber tires, the next steps are the same for all mosquitoes. What normally takes an hour is shown here in time-lapse. The outer shell of the eggs hardens and darkens. With the next rain comes a transformation. In a chemical response to submersion, the eggs hatch en masse, producing mosquito larvae struggling free of their shells. Larvae instinctively swim to the surface. They breathe air through snorkel-like tubes as they siphon microscopic particles of food into their mouths below. For many mosquitoes, this will be the longest stage of their lives, lasting anywhere from a few days to a few months. But a metamorphosis is coming. The new form, called the pupa, will push out of the larval case as 2 small breathing trumpets sprout from its head. The old skin is shed, and the pupa springs to the surface to breathe. For 2 to 3 days, the pupa seems inactive. It doesn't eat. It doesn't appear to move. But inside the case, it's using all its energy to develop into an entirely different organism, a creature with wings and legs and newly developed organs, an adult mosquito. Its head rises from below the water's surface. It shakes off the pupa case. About 10 minutes later, emergence, finally free of its underwater realm. A wobbly but fully formed mosquito. For its first act, it walks on water. It weighs so little, the mosquito doesn't sink. An hour later, after the mosquito darkens and dries, it takes flight in search of its first nectar meal. This cycle from egg to flight is repeated on average every 10 days. That's as many as 50 new generations in a single year. With such a high reproduction rate, it's not surprising that we can do so little about controlling them. The war against the mosquito has been marked by a series of victories and defeats on both sides, and often it was a battle led by real military forces. One key win came about as a result of a famous yellow fever outbreak during the construction of the Panama Canal in the late 1800s. The French began the project in 1881, and right from the start, yellow fever felled workers. Within 8 years, the disease had so decimated the workforce that France was forced to abandon the project, surrendering to the disease that had claimed more than 20,000 lives. When Americans took over the project a decade later, they faced the same deadly threat. But a team of scientists had made a breakthrough discovery at the end of the 19th century, the discovery that yellow fever was spread by Aedes aegypti, a mosquito that bred in standing water near where people lived. One of the scientists was Major William Gorgas. He led the U.S. effort in Panama to get rid of yellow fever by eliminating the mosquito's breeding sites. His teams drained ditches and emptied water-filled containers, and with the disease in check, construction of the canal moved forward and was completed in 1914. While Gorgas helped revolutionize the battle against the yellow fever mosquito, there were many other species and other diseases yet to be fought and strategies to be devised. During World War II, in Asia and the South Pacific, soldiers ran the risk of more than enemy bullets as malaria took thousands of lives. Training films used humor to put soldiers on guard against the invisible enemy. The mosquito was another kind of dive bomber. With so many soldiers in harm's way, the U.S. military began intensive research well beyond the mosquito net to fend off the mosquito. What they discovered was the repellent DEET, diethyltoluamide. DEET was the personal equalizer in the fight against mosquitoes. And soon after World War II, it found its way into commercial use.
Now you can end the...
Ever since the 1950s, people around the world now spend millions of dollars each year to keep the female mosquito at bay. At the Walter Reed Army Institute for Research in Washington, D.C., the U.S. military's research efforts continue to this day. DEET is still the best we've got, but scientists are worried. Some malaria mosquitoes aren't repelled by the compound, so the search continues for a better and even longer-lasting defender. The testing is done with human blood. Each pool is coated with a different concentration of the compound being tested. Then, hungry females are let in. Repellents work by confusing or disrupting the mosquito's chemical detection system, effectively blinding them to the presence of a blood meal. A lab technician observes which concentration of repellent works best. The results will determine whether the chemical is a breakthrough or a bust. The final stage of testing is done on humans. Major Mustafa Debone, chief of the Institute's repellent research, demonstrates the process using DEET.
This is the current standard military repellent we use in the system. The 30% DEET active ingredient.
One arm is treated with repellent, the other is not. Small plastic boxes full of hungry mosquitoes are strapped to the major's arms. When the doors are slid open, the mosquitoes are face to face with lunch. But on the arm with repellent, they're not biting.
The mosquitoes right now, they're trying to move away, the stimuli from the repellents, the vapor that's coming out, they're trying to get away from it. And that's what's going on when you see it right there in the box, in the cage. As opposed to the one that were here, every circle there, you can find at least 2 or 3 mosquitoes biting. And there are like 15 in this cage. Right now, they're so happy because they're getting all that blood meal to produce some eggs.
While DEET may be the best current answer to keep from being bitten, it's not the long-term solution to mosquito-borne diseases worldwide. Along other battle lines, attempts have been made to wipe out the mosquito altogether. Perhaps the biggest breakthrough came in the 1940s. It was a chemical, dichloro-diphenyl trichloroethane, DDT. First tested in World War II, this insecticide became the atomic bomb in the battle against bugs. For many decades, its use was widespread, a worldwide chemical assault from Europe to Latin America. DDT helped put an end to mosquito-borne disease in many industrialized nations by the 1950s. Unfortunately, DDT attacked more than just mosquitoes. It entered the food chain, causing great harm to birds of prey and other animals, threatening some with extinction. To make matters worse, some mosquitoes fought back through evolutionary adaptation.
It was the only pesticide available not only for mosquitoes, but for roaches, fleas, and anything else you can think of. We really didn't know anything about resistance. And within a short period of time, mosquitoes were able to develop resistance to DDT to the point where it was absolutely useless against them.
New chemicals were created, but again and again, the mosquito would adapt and rebound. In the industrialized West, it was a simple change in lifestyle during the 1950s that began to turn the tide.
We don't live outside. We have screened houses. We have air conditioning. Perhaps we barbecue once a week, but much of the week we're sitting in our offices. The whole equation has been tilted away from the probability of transmission.
With fewer people getting infected, the rate of transmission dropped so low that the parasites eventually died out. The mosquitoes that carry disease are still around, but the diseases themselves are currently not. But in most of the developing world, mosquito-borne illnesses never really went away. In too many countries, most control measures, even inexpensive bed nets, the single most effective means of reducing death, are hard to come by or just too costly. In other parts of the world, control stopped because people thought the battle was over. And now the mosquito is making a comeback. The U.S. Center for Disease Control in Atlanta, known as the CDC, has sent a team to the Caribbean island of Puerto Rico to monitor outbreaks of a mosquito-borne killer called dengue fever. In Puerto Rico, as in many tropical regions where an ocean breeze is welcome, air conditioning and window screens aren't that common, so the mosquito has easy access to human prey. In fact, it's a species that has adapted to people. It breeds in their backyards, rests in their homes, and feeds on their arms. CDC entomologist Paul Reiter and his research colleague Manuel Amador have devised an experiment for tracking the mosquito in an effort to understand how it spreads disease. They start with a homemade mosquito buster, house by house, room by room.
What it does give us is an idea of the number of adult mosquitoes that there are per person per house. And as I say, we have also done studies in which we've looked for virus in these mosquitoes, and so we get an idea of what proportion of the mosquito population is actually carrying virus.
Back at the CDC lab, Amador carefully transfers the captured females. Next, he prepares a blood meal. But this blood is laced with a rare chemical called rubidium chloride. It's harmless, but will be absorbed into the mosquito's eggs, providing the scientists with a chemical marker. After they've finished feeding, these mosquitoes will be released back into the neighborhood where they were collected. The CDC team places containers filled with water in each yard within a half-mile radius of the initial release point. These mosquitoes are artificial container mosquitoes and will travel in search of egg-laying sites, depositing eggs one at a time in many different places, including these containers. 10 days later, after collecting the traps, Amador carefully scrapes the eggs from the paper of each separate container to test for rubidium. The eggs are mixed into a solution and burned in a machine called a chromatogram that determines the presence of particular elements by the color of the flame. This peak indicates that there is rubidium present in the eggs. What this shows is that over a 10-day period, the mosquitoes dispersed throughout a single San Juan neighborhood, depositing eggs far and wide. The bottom line is that these mosquitoes travel much farther and bite more often than anyone ever guessed.
The general assumption when we began this work was that the mosquito didn't travel more than 50 yards in its entire lifetime. What we have found in our work is that the mosquito may range over a square mile or so. To us, this is quite surprising. Not so much the distance, because these insects are very well equipped to fly distances, but because the mosquitoes disperse in all directions. If a mosquito is looking to lay her eggs and is carrying virus, then she's spreading the virus to many people. There was no telling where she'd get to.
It's no wonder mosquito-borne epidemics spread so quickly. And in Puerto Rico, dengue has in fact reached epidemic proportions, roughly 20,000 cases a year. Even Reiter himself has felt the pain of dengue fever.
It's a horrible disease. You have terrible aches and pains. Retroorbital pain is what I read in the literature. I knew it when I had it. It's retro, behind the eyes pain. Of course, everybody has a different set of symptoms, but most generally there's high fever, In my case, the fever lasted for 8 days. I mean, people always try and describe it, but it's like trying to describe what it's like to be in a hurricane. You can't imagine what it's like unless you have it.
Reiter knows that the threat of dengue fever can be found in almost any backyard in the city. Standing water is all the dengue mosquito needs.
Anything that accumulates water in a container, whether it's a bottle or a bucket or maybe a child's toy, anything that will accumulate water and maybe a little bit of leaf material to provide nutrition is an attractive artificial tree hole for the female Aedes aegypti.
In Puerto Rico, the typical reaction has always been to fumigate, but insecticides rarely reach the adult female mosquitoes, who are usually resting indoors.
People have been conditioned for so many years that the response to dengue cases is fumigation, that they feel that that is the answer. Unfortunately, it's not. The simple answer is to get rid of the breeding sites. But unfortunately, it's not that easy to persuade people to do that.
But now the fight against the mosquito has changed gear, with a battery of measures invented by scientists across the world, all looking for the knockout blow. In southern Florida, mosquitoes are no longer a major vector for disease, but they continue to be a serious pest. In areas that would otherwise be uninhabitable, control teams are using a technique known as impoundment.
All of these salt marshes, there's an earthen dike that's put around the outside of the salt marsh, and in the wintertime we let the marsh go dry, and then in the summertime we fill it up with water, only to a certain level, and what that does is it denies the female salt marsh mosquito a place to lay her eggs. It's a very effective physical method that does not impact the marshes severely, and it really limits the amount of pesticides that we actually have to use.
Where impoundment isn't possible, Curtis sends out a team with a new biological weapon. Spray guns, loaded with a synthetic hormone, attack the mosquito in the larval stage. Larger areas are treated by airplanes, which drop corn kernels laced with a lethal bacterium.
One of the materials that we use is a juvenile hormone that interrupts the developmental cycle of mosquitoes, and it's very specific for mosquitoes. All insects, as they're growing up, have a whole set of hormones that they use to trigger them to go into a next stage. And the material that we're using tricks them, and it makes them think that they're teenagers for pretty much all their life. It is overloaded with this juvenile hormone, and when it pupates, it stays in the pupal stage and then never develops any further than that. Very, very effective material. It's very safe. It's one of the few materials that you can actually put into potable water around the world, and it can be consumed by humans.
In all of these control methods, speed is of the essence.
We only have about a 3-day window from when the egg hatches until we hit the pupal stage. We're very much like a fire department. We may sit around and not have a lot to do for a few days, but then when we get a rain or a high tide that comes into a salt marsh like this, the field crew has to really work fast.
If an outbreak does occur and adult mosquitoes invade neighborhoods, then a last resort comes into play, spraying with insecticide to kill the adults. But it's not very effective. It only works when mosquitoes come into direct contact with the airborne mist. Some scientists are looking for alternatives to chemicals and other synthetic weaponry. Natural predators may be one solution. At the John A. Morenin lab along Florida's Gulf Coast, entomologist Eric Schreiber is testing one such predator on a local population of mosquitoes.
Okay, this is a typical mosquito lab in here. We raise 2 different species of mosquitoes that we're interested in, and we're interested in trying to work on non-chemical ways of controlling them.
They're also raising a microscopic predatory creature that eats mosquito larvae. It's called the copepod.
The copepods that we study here are crustaceans, meaning that they're related to the crabs, the shrimp, the crayfish. And what they do is they will feed on eggs and the hatching larvae in the container habitats such as tires and different containers people have in their backyard. And they just go ahead and pounce right on them and munch them down.
Copepods may be lethal to mosquitoes, but they're not harmful to the environment in any way. Schreiber loads them into sprayers and heads out into the woods near the lab. He's placed a pile of old tires on the ground to test the effectiveness of the copepods in a realistic environment.
Yeah, so you put the material inside these containers, the copepods in it, they'll eat the developing larvae. As you can see, if I just disturb some of these tires right now, there's quite a few mosquitoes actually flying around. You come out here, it is labor intensive, but you only have to treat once. If you used a chemical treatment, you'd have to come out and treat every 5 to 7 days.
Copepods naturally reproduce, but their range is limited. Today, despite all the latest methods, despite better understanding and new control programs, mosquito-borne illnesses are still on the rise all around the world. In 100 nations, from Brazil to Burundi and all the way across the Indian subcontinent. Scientists battling malaria are especially concerned. Molecular biologist Ken Vernick has been charting its spread.
Malaria transmission is really exploding in the world now. Transmission is out of control. Insecticides that were once effective against the mosquito vector now no longer work. The vectors are resistant. Drugs that used to be effective to treat people are now no longer effective. There's a region in Southeast Asia where there's a new parasite that in fact does not respond to any drug that we have.
With no clear solution in sight, the World Health Organization predicts that the rate of malaria will increase globally more than 15% in the next few years alone. At New York University,